We've all seen the demo. A machine scans a medical image, and in 2 seconds, an AI spits out a diagnosis that took a human doctor 10 years to learn. These algorithms already operate in hospitals today, sifting through patient data and influencing life or death decisions on real wards. The challenge is separating the algorithms that have genuinely earned their place from those quietly endangering patients. The gap between performing perfectly in a research lab and actually keeping a patient safe is the most urgent problem in modern healthcare. In 1975, at Stanford University, a researcher named Edward Shortliff built a computer program called Mycin to diagnose bacterial blood infections. In formal evaluations, Mycin recommended antibiotic treatments at a level comparable to, and sometimes better than, the infectious disease specialists it was tested against. Despite outperforming the human doctors, Mycin was never used to treat a single patient in a real hospital ward. The system failed to cross the threshold into practice because of the surrounding friction. There was no legal framework for assigning liability when a computer made a mistake, and asking a doctor to interrupt their workflow to type text into a massive 1970s mainframe was practically impossible. Mycin taught us a hard lesson early on. Clinical accuracy is useless if the tool cannot seamlessly integrate into a physician's daily routine and legal reality. In supervised deep learning, you feed a neural network a massive set of labeled examples, adjusting parameters until predictions match the labels. This creates a vulnerability, distribution shift. If deployed in a new hospital with different patient populations, the model breaks. By the mid-2010s, IBM had invested an estimated $4 billion into Watson, marketing it to 230 hospitals globally as a definitive cancer treatment advisor. Then, internal documents leaked in 2018 revealed a massive problem. Watson was generating unsafe treatment recommendations. Developers fed it synthetic, hypothetical patient cases mixed with the personal treatment preferences of a tiny handful of specialists, rather than broad, population-level clinical evidence. Staggering financial investment and widespread hospital adoption are not proof of safety, especially when you ask an algorithm to solve a problem as broad and complex as individualizing cancer treatment. Around the same time, hundreds of American hospitals rolled out the EPIC sepsis model. This was an algorithm built right into the electronic health record system, and the vendor's internal testing claimed it was highly accurate at predicting sepsis. Positive predictive value shows how many alarms are true. Applying AI where a disease is rare guarantees false alarms. In 2021, researchers found the EPIC model missed 67% of sepsis cases. Its PPV was 12%, drowning doctors in false alarms. Investigators also found a major flaw in its design: data leakage. One of the variables the AI used was whether a doctor had already prescribed antibiotics. The EPIC model wasn't independently predicting sepsis. It was just noticing that a human doctor already suspected it. Trusting internal accuracy numbers without calculating the actual prevalence of a disease in your own clinic leads directly to alert fatigue and compromised patient care. The successes in medical AI look entirely different. In 2018, the FDA granted its first ever clearance of a fully autonomous diagnostic system, an algorithm called IDXDR, designed to detect diabetic retinopathy. IDXDR didn't succeed because it possessed a more advanced form of intelligence than Watson. Instead, it worked because its scope was hyper-narrow, relying on a single task with an unambiguous ground truth. But we have to be precise about what FDA clearance actually means. It proves a tool is accurate against a specific reference standard. It does not prove that using the algorithm will save a physician time or improve long-term patient outcomes. An AI algorithm only becomes genuinely safe when its clinical ambition is actively restricted to a narrow, mathematically verifiable reality. So how do clinicians protect their patients moving forward? They need to ask 3 distinct questions. Has the tool been externally validated by an independent hospital? Does the positive predictive value hold up against the local clinic's actual disease prevalence? And does the task have a narrow, undeniable ground truth? Answering these questions helps defend against automation bias, the tendency to uncritically trust a confident answer simply because it arrived from a computer. This is critical right now. The rapid rise of broad, open-ended large language models is tempting the medical field to repeat the exact mistakes made by Watson for oncology. Because these newer tools sound incredibly confident across such a wide variety of subjects, the rigorous discipline of scoping limits and tracking honest metrics is more vital now than ever before. A 2-second diagnosis looks like magic, but that magic is an illusion unless it's supported by the invisible scaffolding of external validation and narrow scoping. Anyone can build a machine to give an answer that fast. The real work is checking if that answer is true before a clinician starts trusting it. In the end, the most powerful tool in the exam room isn't the algorithm, it's the clinician who knows exactly when to question it.